Good morning and welcome to this third lecture in the series on model-based fault diagnosis. Today we are talking about fault identification and fault estimation. In this lecture we are going to cover how to design observer for extend the fault detection approach we have seen in the previous lecture to fault identification and estimation. And then we will show how to design thresholds and how to estimate parameters for fault estimation. Before going through details, let us provide some context and see where we are in our path from having a fault event to getting to new operating conditions and accommodate the fault. So you see here also the parallel with what medical doctors do. And so what medical doctors do is covered by this part here, so the diagnosis part. And inside the diagnosis part, you have two steps: detection of a fault, that is falsifying what we call the null hypothesis, and fault isolation and estimation. So once you have detected that you have a fault, so once you know that your patient has some disease, you want to know which one. And also you want to know how severe is the disease, how big is the fault magnitude. So all these questions are answered by this second part, the fault isolation, which means taking the symptoms that you have and classify according to a knowledge base of a number of faults that you know. So the doctor can tell you if you have one or several others of the diseases that he knows about. And then the second step is estimation. So you want to know how big this is. So let us see how we can extend the observer-based approach we introduced last time from detection to isolation and estimation. So in the other lectures we said we covered the first step, detection. So we know how to test and falsify the null hypothesis. Now for isolation, we need to test n fault hypothesis, one for each of the faults we know about. So we assumed from the beginning that we have a knowledge base of faults, and this knowledge base has n elements. So in the case of your car, for instance, you know about a number of faults that can occur in the engine, a number of faults that can occur to the wheels, and so on. Altogether, this is your knowledge base. And we assume there are n elements there. For each of these elements, we have a corresponding hypothesis. And the hypothesis is asking, is the system behaving as if that fault is present? And we need to either confirm or falsify it. Well, actually, the only thing that we can do is to falsify it. Confirming an hypothesis is a nil-post problem, because if you get new evidence, an hypothesis that wasn't falsified before can be falsified later. So if you're interested in this aspect, so there is an epistemologist, Karl Popper, that wrote a very interesting book about the fact that in science, you can only falsify hypotheses. You cannot confirm anything. What seems true until today can be falsified tomorrow. But something that has falsified is falsified forever. And this is actually what we are going to do. We are trying to falsify these hypotheses, but until we falsify them, we cannot say anything for sure. We will see and show it maybe later with an example. It will be more clear. Anyway, after step 2, we have step 3, which is the identification estimation. So we want to know and characterize how big is the fault. And this will make more sense once we introduce a model of the fault. And this model, we have parameters, and these parameters will tell us how big the fault is. So indeed, the problem will then be shifted to estimating those parameters. There could also be the situation, anyway, where the behavior, where the symptoms that you see are not matching any of the faults that you know, which means you can end up in the situation where you falsify all these hypotheses, but still you know that you have a fault. So the thing that you can conclude from this is that you have a fault of a new type, which was previously unknown to you. And when this happens, you want to identify a model of that, because you want to add that model to your knowledge base. So at this point, you have yet another problem, that is to identify a new model of a fault. All right. So we said that we want to extend the observer-based approach we presented for detecting fault to these new problems: isolating, estimating, and identifying faults. How can we do that? Well, let us look at the basic block we introduced. So the basic block is this one. We take observation from a plant, we generate residuals, we generate a threshold, and then we test. We check if, in our case, the absolute value component-wise of the residual is crossing the threshold component-wise. So with this approach and with this basic scheme, we can test one hypothesis. We tested the null hypothesis. Now, it shouldn't come as a surprise that to test n hypothesis, to implement the isolation step, you simply replicate that basic block n times, one for each of the fault hypotheses. So in a scheme that is doing both fault detection and fault isolation, you end up with n plus 1 hypothesis, which means n plus 1 blocks. Anyway, still, there are two approaches to falsifying the additional n hypothesis. The first one is the dedicated observer scheme, where each block, each observer, cannot falsify its own hypothesis, but will falsify the hypothesis of all the other remaining blocks. The other approach, which is the other way around, is the generalized observer scheme, where each block can falsify his own hypothesis. So if you think about what we did last time, we did this. So we had a block for falsifying the null hypothesis. And for the isolation step, we will continue this way. So we will use the generalized observer scheme. And there are several reasons for doing that. And one of the reasons is that designing observers that can do this is something that is not always possible. So it depends on the structure of the system, can work basically for linear systems in nice conditions. But this one we can always generate. So this approach is going to work also for nonlinear systems, at least in the situation that we are considering now, the situation where we assume that we have full state measurement. And so this is what we are covering today. Okay, still, we have a problem. So the problem is that if we have these n plus 1 blocks, how do we take all the results from these blocks in order to formulate a final diagnosis of the system? So let us see how to answer this question. So first of all, we said we are taking blocks like that. One is going to implement the fault detection estimator, but actually now the name is a little bit different. So this is FDAE, fault detection and approximation estimator. So don't worry too much about the approximator part. We will see in the next lecture what it does mean. But for now, just consider this is the estimator, the observer for detecting a fault. We add a number of estimators for isolating the n faults, and we connect them this way in an overall architecture for doing fault diagnosis. So you see that we have the plant, and the observations from the plant are fed to each of these blocks. So all these observers are using the same data from the plant to compute residual and thresholds and to evaluate their logical test. And the output of each of these blocks is a yes or no to this kind of question. Is the null hypothesis false? Is the hypothesis of fault number 1 false? Is the hypothesis of fault number 2 false? And so on until the fault number n. All these hypotheses are taken together in a block that is implementing the isolation logic. And the isolation logic is looking at this condition, the condition where every one of these hypotheses has been falsified but one. Why we want to do that? Because if we end up in this condition, it means that of all the possible explanations for the symptoms, we rejected everything but one. And this one, the only one that we didn't falsify, is, up to that moment, our explanation for that fault. So it is isolating the fault that is present. But anyway, as I anticipated before, there is a caveat. So, as we said, we can only falsify things. So if we falsified everything but one hypothesis, that one surviving hypothesis is telling us that up to that moment, with that evidence that we collected, it is not impossible that that given fault is present. Okay, that's quite long. But the fact is, you never know. If you get more data, it can happen that you falsify also that last hypothesis. And then you have a new kind of fault present. This is always possible. Okay, there is still one thing to say about this block, because there are some arrows I didn't introduce yet, and there are these arrows. So the output from the detection observer, so the answer to the null hypothesis testing is used to drive the isolation blocks. How? This is an enable signal. What you see here is an enable, which means until you falsify the null hypothesis, there is no reason to activate these observers. Also, because it will not make sense, because when the system is healthy, all the hypotheses will be falsified, because no faulty behavior will match the healthy behavior. So there is no reason to run those. And so from that moment on, when you know there is a fault, then you start isolating it, which makes sense also from a computational point of view. You need to consider that all these observers have a model of the system, and these green ones also have a model of the fault, and they need to be run in real time. So there is no reason to waste so much computational resources. So you keep them off until you have a fault. So this can make some sense, hopefully, for you. But still you may have a big question. So what is inside these observers? So how are they going to match the behavior of the system during a specific fault? Well, the answer is that the observer that you have here and here and here, they are built using a model of the plant when that given fault is present. So you have one model here representing the nominal healthy dynamics, and here you have different models. This is representing the dynamic of a system with that given fault. And so we will see in the next slides how to build these observers and how to use them not only for isolation, but also for estimation of the fault parameters. But before going into equation, let's have a final qualitative look at about how the scheme is supposed to work and how we're going to combine the results from these blocks and the fault isolation logic. So if you look at the residuals produced by these blocks, you are expecting to see something like this. Let us start with the detection observer. So at some time t0 we have a fault. Before that, the residual, the absolute value of the residual component y's was below the threshold. And this is by design. So we are sure about that if we have a deterministic threshold. We have a high probability this is true if we have a probabilistic threshold. After the fault, anyway, we are expecting the residual to grow and here to cross the threshold. So at this moment, we falsify the null hypothesis. We know a fault is present. And so this is what we call the detection time. At detection time, we turn on all the isolation estimators. And then it can happen something like this. So you have the residual from this isolation estimator that eventually is crossing its own threshold. So every block has a different threshold. At this moment, what you do is that you exclude that fault. So you falsify the corresponding hypothesis. So you know, with the evidence you have so far, it is not possible that fault number 1 is present. And then you can have a behavior like this for fault number 2 instead. The residual is always below its own threshold. So you never falsify hypothesis number 2. And then, for all the other faults, you can have this behavior, like for fault number 1. The residual eventually is crossing its own threshold. And so at this time, you are excluding that hypothesis, that fault as well. But this is the situation we like, because we ended up exactly having all hypotheses but one falsified. Which means that if you take the latest between all these exclusion times, that is the time you isolate fault number 2. Of course, this is the ideal situation. As we said, we stressed that again, you never know, later you can cross the threshold of fault number 2 as well. Okay, at this point, I guess we are ready to go into details and look at the questions. The first thing that we need to do is to define the knowledge base before building the isolation observers. So we said many times we have this knowledge base, we have this knowledge about the faults, but how do we mathematically define that? We define that through a set. We call it the fault class, and this set has several elements which are fault functions. Because you remember, we model the system with a fault using an equation like this in continuous time. So we have a nominal dynamics plus the uncertainty. Let me write it as with a short notation, plus the function beta, the one that is describing the time evolution of the fault, times the function phi of x and u and time. And this function phi is the one that is describing the shape of the fault. So every fault is going to have a different one, and all the possible different phi of the faults that we know will be stored here. So we have a phi for fault number 1, 1 for fault number 2, and so on. And this, well, this makes sense because we describe things with models, with functions, and then our knowledge base is described using a collection of those functions. Anyway, we assume that we have a particular form for these functions. So they are not completely general, but every one of those functions can be actually written in a form like this. So every function is a vector field. So you have n components, n as the dimension of the state. So we remember that state x belongs to Rn. So we have n components for this function to define, and each one is defined as a product like this. You have yet another function, g, of x and u, and possible of time. And this is the function that describes the shape of that particular fold. The magnitude of that is encoded by a parameter vector theta that is in front of that, and it is multiplying it. And this is similar to approximating an arbitrary function using an expansion in some series, like in Fourier series. So you may assume that this function can be written like this. So it can be alpha 1 that multiplies the cosine of x plus beta 1 that multiplies the sine of x plus alpha 2 that multiplies the cosine of u plus beta 2 that multiplies the sine of u. Yeah, this is just a made-up example, so you can have higher order terms, or you can have other type of basis functions, but the idea is to write a function phi like this. And these alpha 1, beta 1, alpha 2, and beta 2, they are going to end up here. So the parameter theta, in this case, would be alpha 1, alpha 2, beta 1, beta 2. So this is the idea. And the reason for doing that is if you have a fixed form of the function with parameters that are multiplying individual terms here, it is easier then to estimate just the value of these parameters. So this is an example where we have quite a general form. Actually, you can have also a very specific one. So the behavior of your fault can be something that you can model using first principles, and we're going to see later some examples. By the way, in this case, the function g is going to be a vector itself with these components. So you have cosine of x, cosine of u, sine of x, and sine of u. So you easily see that if you multiply theta by g, you get this expression here. So at this point, you need to imagine that the fold class has a lot of these. And every g has a different shape, and the parameter theta is different. They don't need to be the same size. So phi has n components, but the components of g can be anything that you like. So if you need 200 terms to approximate this fold function using an expansion like that, well, you use 200 terms. So the only thing that we need to assume in order to have a problem that we can solve in practice is that the parameters vector cannot take arbitrary values, but they need to be part of some set, big theta, And this domain for the parameters is describing what are the possible magnitudes of the fault for that specific fault. So you don't assume that a given fault can have any possible magnitude. There is a maximum one that makes physical sense. And you know that there is no way that you have a fault bigger than that. So if you remember the case where we defined a fault acting on an actuator, and we wrote it this way. We said the faulty actuator signal is equal to 1 minus alpha that multiplies u. Okay, this is modeling a reduction in the effectiveness of the actuator. So alpha can be between 0 and 1. There is no reason to model alpha being bigger than that, because a fault is not making your actuator more powerful. It is only going to make your actuator less powerful. So in this case, this big theta, so first of all, the parameter theta would be just alpha. The function g would be minus u. And this big theta would be the interval 0, 1. So in this simple case, it's quite easy to see how to define that. More complex cases, maybe it's not like that. But this is a fundamental hypothesis, because you will see later, we need this in order to be able to isolate between different faults. Now that we introduced this assumption that is defined the way we are solving the problem, we need some definitions. Definitions about time instants. Time instants that actually we already saw before in this example. So we need to define these times, the detection, the exclusion times. The detection time we already defined in the previous lecture. It's now time to define the fault exclusion time. So the fault exclusion time, K, E like exclusion, L, upper index, for fault number L. So the index you have here is this one. This fault is defined as the earliest time instant. So we are in discrete time now, so we are defining time through time instants that are discrete. So K is that. So it is the earliest time such that there is one component between all the n possible components of the residual, such that the residual, that component in absolute value, is crossing the threshold, the same component of the threshold. So now look at the notation. So as we have n possible fault isolation estimators, we denote quantities belonging to a given estimator using an upper index. So the other time instant we need to define is the isolation time. The isolation time that is here. And it is the time at which we isolate a given fault. So the fault number S is isolated at a given time, okay? If for all the others, so for all the L that are belonging to 1 to n except S, we have that their exclusion time already occurred. So this is a way to say that at time k, all the others have been excluded. And furthermore, we didn't exclude that fault yet. So we don't have yet an exclusion time for the fault number S. At this moment, then we say we isolate that. So we are just writing down formally what we said before. We isolate a fault when we exclude all the hypotheses but that one. And the isolation time is, sorry, there is a mistake here. It's not the minimum, it's the max. So The latest exclusion time between all the others is the time at which I isolated that given fault. So let us assume we have 3 faults. The first one is excluded at 1 second. So KE1 is 1. The second one is excluded at 2 seconds. That is KE2 is equal to 2. And the third one is never excluded. Well, this means that we isolated the third one, and its isolation time is the biggest between all the others exclusion times. In this example, 2. So having made our assumptions and our definition, we can now introduce the equations for the observers for fault isolation and estimation. So what is inside the green blocks that we presented before, the FIE? So we have estimators like these ones. We have an equation where the estimate for the estimator number L, so we have the L index here, is equal to, as before, we have the nominal dynamics computed using measurements. We have the output error feedback term, like in the previous case, like in the detection observer. But then we have a new part. And the new part is this. This is the model of the fault. So this is how we make every FIE estimator specific to a given fault. We put the fault function here without any beta in front of that, because we are assuming simply that the fault is there. We don't know how it's going to evolve over time. We are anyway accounting for that by this parameter, theta hat, that is the current estimation of the magnitude of the fault. So if the fault just occurred and the beta in front of that is almost 0, well, we can account for that by having a value here of the parameter that is small. This is as we assume that a smaller value of this parameter will produce a smaller magnitude of the fault. But that's quite a reasonable assumption considering the definition we introduced of the fault function phi as a product between the parameter vector and the shape, the structure function g. So once more, let's stress that this is the function phi L, the ones that in our knowledge base is the Lth one. And you see that we have a hat on top of that, because this is not the true function, because the true function depends on a value of the parameter that we don't know. Nobody tells us before which is the magnitude of the fault that is going to occur. So we don't know, we have to estimate. That's the whole thing about that. And so we put a hat to denote this is the function that we are estimating and not the real one. And the function that we are estimating, as we said, is depending on the parameter theta that also has a hat on top of that, because this is a value of theta that we estimate as well. So initially we don't know it. So this term basically is our actual belief about the fault at time k. It depends on time k because as we have new data, we are going to update our estimation of this parameter. And hopefully, after we get enough data, this is going to be close to the real one. So we really hope that we start from some value of theta hat L at time 0. Somewhere there is the true value of theta L. Both of them should be inside a big set that is this one by assumption. And if everything is going right, we start from here and we end up here. So if we can do that, we obtain as a result that we estimate the fault. We estimate the fault magnitude. So this is what we want to do. So you see, that's quite a different thing that what the detection observer was doing. So the detection observer was doing only one thing, was computing a residual that was used for falsifying its hypothesis. The fault isolation and estimation observer is still producing a residual the same way, difference between y and y hat, which still is used to falsify its own hypothesis. But another thing that this observer is doing, as it is an adaptive observer, is to learn the magnitude, to estimate the magnitude of the fault. So this is an extra functionality for this observer, and that will introduce some quite additional equations. We will see them very soon. Anyway, still the idea is that if the fault is matched, which means fault L is the one that is really present, the residual is small, below the threshold. If fault L is not present, we would like R, the residual, to be big and cross its own threshold and falsify that hypothesis. How are going to be the residual dynamics for this new observer? So remember the equations for the system and the observer. Now, one thing. So we have the equation of the system without a fault, but when we turn on the fault isolation estimators, the fault is present. We have detected it. So we need to add it to the equation. Now the question is, which fault are we adding that? So we will now write the residual for the case where we have a matched fault. So we assume that we have the fault number L indeed here. So we have plus phi L that depends on x, u, and theta L. And this is the true value, the true theta L. So if we compute the residual, we know that R at time k plus 1 is equal to y at time k plus 1. So we defined that previously. So R is y minus y hat. L at time k plus 1. So this is equal to x at time k plus 1 plus the measurement noise minus the estimate at time k plus 1, which is equal to, okay, at this point we need to take the difference between this equation and this equation. So we have f minus f, but it is computed with different arguments, so we can't simplify that. So we have f that is computed with, let me drop the indexes here now. We have y minus xi. So x is equal to y minus xi, and u minus f that it is applied to y, the measurement, and u. So this is the difference of these terms. We have the uncertainty that is only present in the system dynamics plus eta. And then we have the difference between this and this. So we have phi computed again with y minus psi, u, and the true value theta L, minus phi computed with estimates. And then we still have plus lambda that multiplies the residual at time k, and still we have this, the measurement uncertainty at time k plus 1. Okay, so let us simplify a little bit this. So we define a delta f for this, delta f of y, u, and psi. So delta F is this difference here, plus eta. Now, let us write these later. We first write these plus, and now I'm interested in writing this. So let me allow for a trick. So instead of writing phi of L in y minus psi, let us first write it as this. So phi of L apply to y, u, and theta L minus phi of L that is applied to y, u, and theta hat L, the estimate. And then actually, to make this equal to what I had here, I would need to add a plus phi of L computed in y minus psi minus this term. So it's a trick. So I add and subtract the same term. And let us write that with a delta. Plus delta phi L of y, u, and psi. And also of theta, the true theta. Okay, I wrote that because I was interested in this. I'm interested in that because we have the same function, phi L. This one is with a hat on top. But the hat that you have here is just to denote that. So we know this is the function of our estimator, is not the true one. But it is the same. It is the same function. It has the same shape. It has the same kind of vector for the parameters. It has the same shape. So I wanted to get to this because I wanted to show that we have now the difference between this with the true parameter theta and this with the estimated parameter theta. And now the assumption that we had initially to write the functions that are linearly parameterized is turning out useful because now we can write this in this way. We have theta L, the true one, minus theta L, the estimated. We take the transpose of everything and we multiply it by the shape function GL of y and u. So now you see that in the residual dynamics, we have one term that depends on the difference between the true parameter and the estimated one. So basically, this is the estimation error on the parameter, which is multiplying the shape function g. And I wanted to write this and to show that we have this term because this will be important in understanding how we design the algorithm for learning this from data. And the key thing is that the error on the estimation is directly affecting the dynamics of the residual. This is the key thing. So let me just, this is equal to this. Okay. So the final thing I want to draw your attention to is that in the residual dynamics, we have several terms that we cannot eliminate. So the delta f, due to the fact that we are computing f with different arguments, will always be there. The uncertainty eta and psi will always be there. So this term, delta phi, that is due to the fact that even phi is computed with different arguments in the estimator. So it is computed using y here. In the real dynamics, it is computed with x. Well, it will always be there, always. But there is one term we can do something about, and it is this one. This is the term that we can make equal to 0. How? If we learn the parameter theta, if theta hat is equal to the true theta, this is going to be 0. And this observation, so this remark is the base for developing a parameter estimation law, as we're seeing in the next slide. Because indeed, what we have in the observer, in the FIE estimator, is this adaptive term. We write it again. One thing, actually, for the component I, it is true that you expand it with this product. So what I have written here is a simplification. So this is actually only correct for one component. But please forgive me for this simplification in notation. Just remember that actually it is this. So our goal, as we said, is to make theta hat go to theta. And in doing that, we can make the residual to be smaller, which is nice, because if indeed that fault is matched, this is making the residual going farther away from the threshold, so we are not falsifying it. Okay. But in doing that, we need to remember that we have a constraint to satisfy. So the theta hat that we learn should be inside this domain. So now the question is, how do we come up with a rule, a law to update theta in order for this to happen? Well, the solution lies in the fact that if we are able to do that, the residual is getting smaller. And so the idea is, can we come up with an update law for this that is making the residual smaller? Because we understand that if we are doing that, this must happen. And especially because of the way that we formulated the problem. So we formulated it like in a way that we have this term here. So if we're making the residual smaller and all the rest is the same, it means this is getting smaller. There is no way otherwise. So this is the key idea. So the idea is to provide the residual with a new role. So previously it was just used for hypothesis testing. Now it is also used for parameter estimation. So actually how we do that? Well, the answer is in the next slide. We implement what is called as gradient descent. So we have our residual. We know that the residual depends on the error on our estimation of the parameter. And then we implement a law for updating the parameter that is making the residual smaller. And the way to do that is to go in the negative direction of the gradient. So you probably have already seen that. If you have a parameter theta to learn, and if you have some goal function of that, and this is nice and this is convex, then a way to learn theta is to start from an estimate of that and move toward the direction the gradient is getting smaller. So you get here and here and here. Maybe you overshoot, then you go this other direction, and you converge here in the minimum. So are we in a situation like that? Well, yes, because you see the residual depends on this. So if we can update the estimate of theta in the direction that we get a smaller residual, we get to our goal that is our, so if this theta hat, the true theta is here. Okay, so now the question is, can we compute this gradient? Well, yes, we can. It's quite easy because the gradient is this function g. So the gradient of the residual with respect to theta hat is actually equal to minus g. You see, we have minus theta L multiplying g. So the gradient with respect to theta, so you do a derivation, so this goes away, and you have minus g. This is what we get as a gradient. As we want to move in the negative direction of the gradient, the minus g becomes g. And we have it here. Now, we have one more thing. So in this gradient descent, we multiply the direction of the gradient descent by two terms that are telling us how big this step should be. And the two terms are these, which is the learning rate. This is a general rate that is governing how fast we move, and it is assuring us that the learning is stable. Because if I take steps that are too big, I will go from here to here, and I will oscillate around this minimum, but will not converge it. In order to converge, I need to take steps that are large at the beginning, but small when I'm close to here. And eventually they become 0, and then I stay here. So the way to do that is to have this term, the learning rate, that is multiplying the gradient. And also we have this other term here, delta r. And this delta r is the thing that is big when I am far away and small when I'm closer. Why? Because delta r, defined here, is equal to r minus lambda r. R at time k plus 1 minus lambda r at time k. Why do we have this term? So the answer is in the dynamics we have written out before. So you see that r at time plus k is all this stuff, including this term due to the learning error. And between all these other terms, we have this lambda that multiplies r at time k. So the idea in introducing this delta is that this delta r at time k plus 1 being equal to r at time k plus 1 minus lambda. Now I write it like this for consistency. Then it is equal to this stuff, this stuff, this stuff, this one, and this. So we remove this part. So the reason basically to introduce that is to have an expression that has less terms in it, because all the terms that are not this one, when we consider our learning problem, they are sort of a distraction. They are things that can make the residual big or small, independently of how good we were at learning theta. So this is a convenient way to get rid of the only thing that we know in the equation. We know r at time k. At time k, we know it, we measure. So when writing the equation for the next value of r, we can get rid of that. And so we make our expression dependent on less foreign things. And so we are getting closer to just having this one. So if we could have an expression where we have only this one, then for learning this is perfect. Because if we learn correctly, that expression is going to 0. In this case, we need to live with the fact that we anyway have these other terms. At least we get rid of this one. So in delta R that we have here, we get rid of that. And delta R is going to be big anyway when our estimation is bad, and smaller when the estimation is good. So we use that to multiply the gradient to make this step bigger or smaller. And indeed, the learning row is defined as steps. It is a difference equation as well over time. So we have that the new estimate of theta at time k plus 1 is a step starting from the previous value of theta at time k plus this correction term going down the gradient. And all of that anyway is enclosed and is the argument of this thing that is called a projection operator. But yeah, a lot of things. But for a moment, forget about the projection operator. It is just telling us new estimate, old estimate, plus the step down the gradient. So this is the main picture. What we are left, and we still need to define, is this gamma, which is the one that is guaranteeing stability of this learning row. So this learning rate, which is time varying also, is equal to this expression. So we have a term on the top, mu, and at the denominator we have two terms, one epsilon plus this norm of the gradient. And so let us forget about mu and epsilon for a while. So if you take this, you plug it here, you see that you have g on the top and the square of g at the bottom. So what is doing that? It is basically normalizing with respect to the gradient. It is a way to keep the direction of the gradient, but not the magnitude of the gradient. And the reason is I want to go down the direction of the gradient, but I don't want to go too fast when the gradient is big, because this is leading to instability. Instead, I want to control my step size mainly by delta R, which is the error in the residual. So how far I am from this. I want to control this step using this one. I don't want to control that using the amplitude of the gradient. But anyway, as I'm normalizing by a norm, this is just making it smaller, but it is not changing the direction. So I'm still going down the gradient. So what are these two coefficients, mu and epsilon, doing? Well, epsilon is some number that is different than 0 and positive. This is to account for the fact that sometimes the gradient can be equal to 0 or very small. So you don't want to get a divided by 0 when the gradient is 0. So we put this here. And mu is a number between 0 and 2. And the reason for is, if you go and look in this book by Goodwin and Seen, Adaptive Filtering, Prediction and Control, you see the proof that for this law, adaptive law, to be stable, you need mu to be between 0 and 2. I mean, you know for discrete time systems that you want eigenvalues that are inside the unit circle. So if you do the stability analysis for this, which is basically a discrete time system, you will see that having the eigenvalues inside the unit circle can be guaranteed if mu is between 0 and 2. And we are not going further into proving that. So we just take it from granted from this book.